So now we go over the second order derivative of multivariable function. So it's very important for you to be familiar with this notation here. So in the actual problem, they can just give you to find this, all this you see on the right hand side. So they give you the function and then they want you to determine this. So you can have this, that, and so forth. So what does this mean? Okay, let's start with the first expression. So it simply means that if you have a multivariable function which is called z, and that function has a variable x and y, so that simply means that you have to derive it first with respect to x, and then you're going to have an expression, and then what you get, you again derive it with respect to x. So you first derive with respect to x, you get a function, and then you derive it again with respect to x. So the second derivative tells us that we first need to derive the function up with respect to y. We get an expression, and then you derive it again about y. So we have this notation here. So this is the same as if I say if I write it like this. So this simply means that I first have to derive the function with respect to x. So I'm gonna get a certain expression, and then I derive what I got again with respect to x. So that can simply be written as second derivative of the function z with respect to x. So same thing for the second expression. So that can also be written as, so you actually need to derive the function z with respect to y. So I'm gonna get something, and then I derive it with respect to x. I mean with respect to y. So this is the same as if I write it that way. So the partial derivative of z with respect to y. So this is actually the second partial derivative. So in the third expression we have the second partial derivative of the function z with respect to y. So that can also be written as the first partial derivative of the function z with respect to y. So I first get the first partial derivative with respect to y, and then what I get, I'm gonna derive it again with respect to y. So this is the same as, so you can write it that way. So it's the same. So and then we have the last expression. So this is the second partial derivative of z with respect to y, and then with respect to x. So what does it mean? So we have a function, we have a multivariable function z, which is made of x and y variable. So you simply need to apply the first derivative of that function with respect to x, so you get a certain function, and then from there you can derive. So you just need to derive that function again, but with respect to y. You first derive it with respect to x, and then you will apply this, another derivative, but with respect to y. So this is the same as if I said so the first partial derivative of the function z with respect to x, and then you derive this expression here with respect to y. But the simplified form is, you can just write it that way. Okay, now let's look at some example. Okay, let's consider the first expression. So here they say we have to find all the second order partial derivatives of the following function. So I have a multivariable function f of xy, which is made of x and y. F of x y is equal to x cubed y4 plus x y cubed. Okay, let's find this one. So we have the second derivative of the function z with respect to x. So it simply tells us that we first need to derive the function with respect to x, and then we'll derive it again with respect to x. So I'm sure you know already, because if you understand the partial derivative, you know how to find the partial derivative of function as we did last time, then you won't have a problem to struggle with this type of question. We will first derive that with respect to x, so while treating y as a constant. So the first term will be 3x squared, and then y4 is a constant since we are deriving with respect to x, and then the second term is y to the power of 3. So I just derive it with respect to x. So again I will have to derive it with respect to x. So that's the first derivative. So we have the first derivative of the function z with respect to x. So now if I derive this function again, I'm gonna have this. So we have the partial derivative of the function z with respect to x, and then with respect to x. So this is the same as second derivative of z with respect to x. So I just need to derive the function that I got. So I need to derive it again with respect to x. So I'm gonna have 6x. So y4 is still a constant in this case. So the derivative of y to the power of 3 is 0 because we are treating y as a constant. So that's the answer to this. Alright, that is the first partial derivative. That is the partial derivative number 1. So we have the partial derivative number 2. So here I'm gonna have to derive the function with respect to y. So for all this step I need to derive my function with respect to y. So we have the second derivative of the function z with respect to y. So here I first need to find the first derivative. So my first derivative with respect to y while treating x as a constant will be 4x cubed y to the power of 3, and then we have the second term will be 3x y to the power of 2. So therefore the second derivative of function z with respect to y will be, so I just need to derive the function that I've got here. So I have 12x to the power of 3 y to the power of 2 plus 6x y. So this is the final answer. So now we need to do the derivation number 3. So here we'll first have to derive the function with respect to y and then with respect to x. So first step, we derive it with respect to y, we get a certain function, then we derive that function with respect to x. So working on the same function, so we have f of x y is equal to x cubed y to the power of 4 plus x y to the power of 3. So again we first need to derive it with respect to y. So if we apply the first derivative of this function, we get so we call this function z, or we can also use this notation here. Just say first derivative of the function f with respect to y. So the first derivative will be 4x to the power of 3 y to the power of 3 plus 3x y to the power of 2. So now what's gonna be the second derivative? So I just need to derive the function that I've got. So we have the second derivative of the function f xy divided by with respect to y. So that's gonna be with respect to x. So that gives 12x squared y to the power of 3 plus 3y squared. So here the trick is to understand this for derivative. So if they give you this, immediately you need to understand that you have to find, you need to apply this relation here. So and then we have the last one. So now what's gonna be the second derivative of the function f of x y with respect to y and then with respect to x. So here we first derive the function with respect to x. We get a certain function, and then we derive that with respect to y. To derive it with respect to y, we get 3x squared y4 plus y to the power of 3. And then we now derive it with respect to y. So if we derive the function with respect to y, in other words, we are determining this expression here. So that gives 12x squared y to the power of 3 plus 0. So actually you need to have 3y to the power of 2. So you are going to notice that these two expressions are identical. So you can start with x and then you end up with y. So that is the same if you start with y and then you end up with x. So we have another example here. They want you to show that the second derivative of the function z with respect to x and then with respect to y is the same as the second derivative of the function z with respect to y and then with respect to x. So that's gonna be your homework, but I'm gonna give you some hint. All you need to do is you take that function, you apply the second derivative of that function with respect to x and then with respect to y. You're going to get a certain expression. So now you do the same for this function here. So you apply the second derivative, you're gonna get the expression here. So at the end you are going to notice that this expression is the same as that one. So if they are not the same, then you need to check your steps. So now let's go over some application of partial derivative. So the first application is, so they are actually used to determine the volume change of, so it can be the area's volume change of certain shape if the sides are subjected to a certain change. Like in this case, okay. So this is actually a problem where we have to find the volume of a cylinder. So it means the change of volume. If because the volume of the cylinder is determined, can be obtained from the height, the radius, and yeah, it's actually the height and the radius. So what's gonna happen if the height and the radius undergoes a certain change? So that's gonna also affect the volume. So here we are given the radius and the height. Let's say if r changed to delta r, so that simply means that we have the radius, which is r, so that is the initial radius. So now if the radius undergoes a certain change, so the final radius will be given by the initial plus the change of the radius. So if that change also appear to the height, so the final height will be equal to the initial plus the change in height. So the volume also will undergoes such a variation. So the actual volume will be equal to the initial plus the change in volume. So that change in volume is given by this relation. So we actually have to use the actual value of radius and the actual value of height. So the actual value of radius is given by this expression here. So we have r plus delta r, and then the actual h is given by h plus delta h. So now if we expand this expression here, so if you first expand, so you first expand this part, and then you expand, you multiply it by h plus change in height, so you are going to get this long expression here. So now in this expression you are going to notice that they have neglected some term. You can see that they have neglected some term, like this term is neglected, and that one is also neglected. So if you simplify this expression, so it's now reduced to this one here. To actually have the change in volume, which is equal to pi r square, the change in height, plus 2 pi h multiplied by the change in r. So the reason why we have removed some terms is it's because they are negligible. So now if we have the formula of the volume, which is given by pi r square multiplied by h, so if we work out the partial derivative of the volume with respect to r, with respect to h, so I'm going to get pi r square, and then if we try to find the partial derivative with respect to r, so I'm going to get 2 pi r h. Okay, we have learned how we went from the expanded expression to this one. So the change in volume is given by this relation here. So in this relation, I will notice that, so the relation is the change in volume is equal to pi r square h plus 2 pi r h multiplied by the change in r. So now at this stage I can just replace this relation here. So I can just substitute pi r square in the first term. So here you can see we have a pi r square. I can replace it by the change in volume divided by the change in height. So therefore the formula will be the partial derivative of the volume with respect to h, and then I multiply it by the change in h, so that should actually be the change in h. So similarly for the second term, I realize that I have this expression here which can be substituted by the partial derivative of the volume with respect to the radius. So I actually have the change in volume divided by the change in radius multiplied by the change in radius. So that's how the change of volume can be determined if the height of the cylinder as well as the radius undergo a certain change. So now what is the general equation to compute the change of a function? So in general, if we are given a function that is made of two or many variables, okay, let's assume that we have a function f of x and y. So in this case, we only have two variables. So now the question is, if the variables undergo certain change, what gonna be the change that this function will undergo? So we just use this relation here, which we can call that function as z. So the change of the function z is given by the partial derivative of the function z, so with respect to the first variable, and then we multiply by the change of the variable x plus the partial derivative of the same function with respect to the y variable multiplied by the change in y variable. So this expression is very useful when I use it in many applications that are going to come. So we are actually referring to this function. So even if you look at the relation of volumes that we have derived previously, we can say that, so here we actually need to determine the change in volume. The volume will change as the height change as well as the radius. So all you need to do is, since you have the function of the volume here, to determine the change of the volume, you just use the partial derivative. In other words, you need to derive the volume with respect to h, and then you multiply by the change in height. So they need to precise the change in height in the problem, plus secondly you're gonna have to do the partial derivative of that volume with respect to the radius, because here we have two variables. The first variable is the height and the second variable is the radius. So you apply this first derivative, you apply the partial derivative here with respect to r, and then you multiply it by the change in radius which they are going to give it. So this is basically the same as what we have here. So make sure that you memorize and understand this relation properly. So now let's look at some application of the partial derivative. So here's the first example. So they want you to use differentiation to calculate the increment in volume and the surface area of a sphere with a radius which is 50 centimeters, and the radius is increased by 0.5 centimeter. So the starting point here is to write down the formula that is used to compute the volume of a sphere. So this is the formula. But if you look at this formula, we only have one variable. So this is not a multivariable function, because we have a function v which only includes one variable r, but we can still use the relation to determine the change. So I'm referring to this one. But in this case, okay, this is the relation that can be used to determine the change of the function. So we have the partial derivative of the function with respect to x multiplied by the change in x plus the partial derivative of the function with respect to y multiplied by the change in y. So in this case we only have one variable, so that means the second term will falls away. So the function is v. So now to determine the change in v will be, so the change in v will be equal to the derivative, the partial derivative of the volume with respect to r multiplied by the change in r. So you don't have the second term because in this case we only have a one variable function, so the function only includes one variable. If we add many variables, for instance 2 or 3, we can add other terms. So now, so this step is completed. So now how to determine the partial derivative of the volume with respect to r? So we actually get this. So we have 4 pi multiplied by r squared multiplied by the change in r. So now from this stage we can replace the variables that is given by the values in the problem. So we have the radius, which is 50 centimeter, and as they say that the radius increased by 0.5 centimeters, so that 0.5 represent the change in radius. So you just need to look at the change in this relation here, and then you replace it, and then when you compute you end up to the change in volume. And the second question, they want you to determine the change in surface area. Well, you first need to know the formula of the surface area of the sphere, which is given by 4 pi r squared. So now after that you're gonna have to write down the formula to determine the change of the surface area. So the change in surface area is given by delta A, which is given by the partial derivative of the area with respect to r, and then multiply by the change in radius. So this part tells you that you have to derive, so you derive the surface area with respect to the radius. So when you derive, you get this expression here, and then at this stage you can just substitute. So you have the change in r, which is given, and then you have the radius. So here's another problem. They want you to determine, or they say calculate the increment in the volume of a cylinder with radius 10 centimeter, height 20 centimeter, and its base radius is increased by 0.02 centimeter, and its height is decreased by 0.03 centimeter. So here you need to pay attention with some words if they say increased or decreased. For increase, that value is, so the change is positive, and negative for the decreased value. So for the decreased values, for the word decrease, so the value should be negative. So for the weight increase, the value should be positive. So that need to be positive, and that one need to be negative. So they want you to determine the change in volume. So in this case, we have the volume which is given by pi r square multiplied by h. So in this case, we can say that this represents a multivariable function because we have two variables. So we have the first variables, which is r, and the second variable, which is h, which is the height. So now both variables undergoes the change. Therefore, the volume will also undergo a change. So if we still use this relation here to determine the change of the volume, so we have the change of the volume which is given by the partial derivative of the volume with respect to the radius, and then multiply by the change in radius plus the partial derivative of the volume with respect to the second variable, which is h, and then you multiply it by the change in h. Okay, if we add more than two variables, let's say for instance another variable, so we'll still add that. For instance, if it's that variable is z, so when I have the change in volume divided by the partial derivative of the volume with respect to z multiplied by the change in z, so we can add as many terms as they are given. So and then you just need to compute the partial derivative of the volume with respect to r and the partial derivative of the volume with respect to h, and then you get this expression, and afterwards you are going to replace. So as you can see here, you are going to realize that here they have added a negative sign simply because the height is decreasing. So the height is decreased, so that's why we have a negative sign, but the radius is increased, so we need to have a positive sign on the change in radius. So we have another question here. You say if z is equal to 5x squared y to the power of 3, so they want you to find the change in z. So still use the same principle. So the change of the function z is equal to the partial derivative of the function z with respect to x multiplied by the change in x plus the partial derivative of the function z with respect to y multiplied by the change in y. So now the next step is you just determine these two from the function that is given, and then you'll end up to this relation here. So we have another question that can be applied to the electric circuit, which is made of the resistors. So this is basically a problem from the exercises of the textbook. So it's question number 4. Or there are many questions. I think there are like 8 questions. So this question are for you. So these are basically the homework that you can try when you are free, and then I will try to check that next week. Okay, let's go over this question here. Let's say the total resistance R of the two resistances. So we have R1 and R2. They are connected in parallel. So if two resistors are connected in parallel, so the formula that is used to determine the total resistance is given by this relation here. So we have 1 over the total resistance is given by 1 over R1 plus 1 over R2. So from this relation I can determine the value of R. So to get R, I'll just use the inverse. So in other words, R is equal to the inverse of 1 over R1 plus 1 over R2. So that is equal to, so I have 1 there, then I find the common denominator, which is R1 multiplied by R2. So on top here I'm gonna have R2, and then here I have R1. So finally I have R1 multiplied by R2 divided by R2 plus R1. So the first step is to write everything in terms of R, because in the problem everything is written in terms of 1 over R. So you first write it in terms of R, and then you simplify the expression. So the simplification just starts from this step to that one. So it's all about simplification. So we actually have a function R which is made of 2 variables. So the 2 variables are R1 and R2. So this function is given by R1 multiplied by R2 divided by R2 plus R1. So it's like I have a function Z which is given by X multiplied by Y divided by X plus Y. But X and Y are replaced by R1 and R2. So now how to determine the change in R? So the change in R is given by delta R, which is equal to the partial derivative of the function R with respect to R1, and then multiply by the change in R1. Since we have 2 variables, then we're gonna have 2 terms. So the second term will be the partial derivative of the function R with respect to R2 multiplied by the change in R2. So the next step is to find the partial derivative of the given function. Okay, I can work this out on the separately. So I have the partial derivative of r with respect to r1. So I have remember that I have the function which is given by r, which is equal to r1 multiplied by r2 divided by r1 plus r2. So the partial derivative of r with respect to r1, so in this case I'm going to need to treat r2 as a constant. So I will actually have to use the division rule of derivative. So I'm going to have, so I have to derive r1 multiplied by r2. So that's going to be the first function that I have to derive. So here you just need to remember that if we have the division of two functions, so we have f of x, which is the numerator, and g of x, which is the denominator. So if you derive the division of f of x and g of x, so when I have to you first derive f of x and then you multiply by g of x, and then minus, you derive, you repeat f of x and then you derive g of x, and then you divide the numerator by g of x squared. You are going to apply this formula here because we actually have a function which is made of the division of two functions. So we have on top we have the first function, and then at the bottom we have the second function. Both functions are written in terms of the variable. So therefore, if we use the first partial derivative of this function with respect to r1, so I'm gonna have this. So I have the first function which is r1, r2. I need to derive this with respect to r1. So if I derive that with respect to r1, I will only get r2. And then I need to multiply by the function g of x. G of x is just the denominator of this function. So in this case we have r1 plus r2, and then I say minus, so now I'm gonna need to repeat f of x as it is indicated in the formula. So f of x is r1 multiplied by r2, and then I have to derive g of x. So if I derive g of x is the sum of r1 and r2. So if we derive g of x with respect to r1, so we're going to get, because we are going to treat r2 as a constant, and the derivative of r2 gives 0. But if we derive r1, we get 1. And then next, we have to square the function g of x. G of x is r1 plus r2. So when I have r1 plus r2 square, so if I rearrange this expression, I'm gonna have, so I have r1 multiplied by r2 plus r2 square minus r1 r2 divided by r1 plus r2 squared. So I can say that there are terms that can cancel out. So I end up to, so we have the partial derivative of r with respect to r1, which is given by r2 square divided by r1 plus r2 square. So now I'm gonna do the same to determine the partial derivative of r with respect to r2. If you manage to find the partial derivative of r with respect to r1, then instead of doing this from scratch, you can say that the partial derivative of r with respect to r2 will be equal to, instead of using r2 on top, we're gonna have r1 square, and then the denominator will just be r1 plus r2, everything squared. So just repeat the denominator. And the next things to do is you have to replace the derived expression into this relation here. So we just worked out this, so we found r2 square over r1 plus r2. So this represents the partial derivative of r with respect to r1, and then we need to multiply it by the change in r1 plus, so we also determined the partial derivative of r with respect to r2. So we have r1 square divided by r1 plus r2 square. Then we need to multiply it by the change in r2. And the next thing to do is to replace all the unknowns that are present in this expression here. Because if you read the problem, that gives the value of r1, or let's say r1 is increased from 210 to 220. So it means that r1 is increased by 10. So that's gonna be the change in r1. But let's say r2 is decreased from 300 to 295. So here the change in r2 will be -5. So use negative for decrease and positive for increase. So we have r2, which represents the initial value. So the initial value is 300. So all you need to do is, so you have 300 square, and then we have r1 represent the initial value. So in this case r1 is 210. So we have 210 plus r2, which is 300. So the change in r1 is the final value minus the initial. So we got 10. And then we have the value of r1, which is 210 divided by the sum of r1 and r2, which is 210 plus 300 and to the power of 2, then multiply by the change in r2. So the change in r2 is -5. So here we have a square. So now you just need to use your calculator and then you punch all this expression and you get the answer. Okay, let me just open quickly the one that I have. So you have 300 squared divided by 210 plus 300 and everything to the power of 2, and then multiply by 10 plus, so the second term is, so you have 210 on top divided by 210 plus 300 squared, then multiply by -5. So that's gonna be the value of the change in R. So the change in R is 3.4562. Yeah, that's it. So there are a lot of questions that you can also try. So these are basically the exercises from your textbook. So you're gonna have to do the exercise 1.2. So the second derivative questions. So from 1 to 4 if you have time, and then you will also touch some application of partial derivative. So you have some application here I'm gonna show you. Yeah, here it is. So it's exercise 1.3. So you can do all this problem in your free time, and then once you're done you can just WhatsApp me. I'm gonna have a look, and then next time I will try to rectify where I see maybe some mistakes. Cool.